Hello and welcome to Big Data Technologies Module 5's discussion. Jumping right in, we'll go over kind of the overview of the module and then talk a little bit about some other cool stuff along the way. So in this module, you're to use Apache Spark to solve some problems. The basic idea is to understand what data frames are in the context of Spark, uh, how they enable parallel programming and why we use them, be able to understand what a resilient distributed data set is, so RDD. I need to correct the slide and probably the course room because it's a data set, not a database, from both an existing and external source. So how do you be able to talk about how you create them from either something that you're loading externally or something that you're potentially doing inline. So Spark to solve problems. So what is Spark? As we've talked about before, it's a high performance framework that enables you to utilize a distributed environment to process data concurrently. Why do you use it? Well, it's a whole lot easier than writing your own distributed program. Frameworks make that a whole lot easier. Before frameworks came along, if you wanted to do something like write a program that ran across a cluster and do some processing that way, you were going to spend a considerable amount of time doing so. It was a non-trivial undertaking. So that's where these frameworks come to be. That's why we have goodness of Hadoop and MapReduce, and that's why we now have Spark as a way of making it easier for people to do those sort of problems. What do we use it for? Well, lots of different stuff. Analytics in general, data engineering, data wrangling, machine learning, graph processing to some extent, and then just pretty much anything that deals with big data. So as I've mentioned probably in the past, if not I should have, we don't do big data processing because it's cool, although it certainly is. I'll go ahead and pop over. Hi, Alpha. I was going to go through Module 5 unless you had some questions. Okay. So Module 5 centers on big data technology, and in particular solving problems using big data. So the idea, the important areas of Module 5 is that by the end of it, you should be able to solve problems using Apache Spark. You should be able to do so in Scala or whatever language, because at the end of it all, you're basically using the Spark API to do the work, and the language is kind of secondary. If your performance depends upon the language, you're probably doing Spark wrong. So it probably means that you're basically using it as a way of just doing Python execution or Scala execution in the cloud versus actually using the Spark API. So by the end of the experience, you should be able to discuss data frames, explain how they're used inside of data or inside of Spark, and how you create them, manipulate them, and so on. It is very much a functional sort of thing. You take one data frame and potentially produce another one, and then set and save it. So you don't necessarily change them per se. You apply operations that cause new ones to be created, and you save those new ones. You also it enables concurrent and parallel programming and distributed programming, which is the goodness of Spark, as well as any of the big data sort of frameworks. Under the covers, driving it all is this resilient distributed data set. It's not a database; it's a data set. So RDDs are distributed data sets. It was a typo from where I copied this from the course room. So basically, the idea is be able to talk about kind of how they're created and so on, keeping in mind that with newer versions of Spark, the guidance is to not use RDDs, rather to use data frames, allowing higher degrees of optimization and caching and performance improvements. So what is Spark? It is a high performance distributed framework that allows you to do the construction of distributed parallel programs. Why would you use it? Well, it's a whole lot easier than writing your own distributed program. Back before things like MapReduce, Hadoop, and Spark, if you wanted to use a cluster of computers, you had a lot of challenging things to figure out. And that's part of why we now have frameworks, is because it was hard, it was error prone. You would often end up in situations with race conditions and deadlocks and all kinds of nastiness that you had to figure out. You had to figure out what to do whenever somebody goes away, because you might lose one of the nodes in your cluster and so on. That's where these frameworks take care of all that stuff for you, and generally speaking, you don't have to worry about it. So when we look at Spark, this sort of visual kind of helps you kind of understand the layers and the types of stuff that is involved. You have low-level APIs. Generally speaking, you stay away from those. That's where RDDs live, and distributed variables. There may be situations where you have to go down to that level, but you should do so only if you can't solve the problem some other way. There's also this concept of the structured APIs, where you have data frames, data sets, and SQL. Those are typically where you spend most of your time. Data frames is what you use most of the time. Even if you're not necessarily aware of it, when you're using SQL, you're really using a data frame. It's just kind of taking care of some of that for you. There's also some stuff that, in addition to what's on this slide, where you have structured streaming. That's the mechanism that you use a micro batch to basically do processing near real time. It's not a true streaming system in that the output is created based upon the execution of essentially a micro batch, so a small batch, not based upon the arrival of some additional data. In a traditional stream processing system, the arrival of an item causes something to happen. That's not what Spark does. What Spark does is runs essentially batch jobs on a small set of data frequently, with a small delay, or a delay of some sort between, depending upon how you configure them. You also do advanced analytics, machine learning, data science activities as well with Spark. It's quite robust in that space, and as well, there's a set of other libraries and a whole ecosystem built on top of it. It has become a very popular computational engine, regardless of the workload that you're trying to do, to the point that a lot of tools will enable you to target Spark as the place where your processing occurs. Some key words to kind of work through, and the concept. RDD is a distributed assortment of objects that are essentially divided into logical partitions that are going to be processed on a particular node within a cluster. So it's essentially pointers to, maybe not necessarily the data, but pointers to the data that has been assigned to a particular cluster item, a node in the cluster to work on. It is resilient. That means that that's the first bit of the RDD, right, is resilient. And what that means is that if something bad happens, if something becomes disconnected, something goes away, gets sick, or whatever, dies, one of the other nodes in the cluster can pick up what one of the nodes that went away was doing without having to restart the entire processing. So you can basically reconstruct what was going on, because the driver node knows what that particular node was assigned to do. It knows what it was supposed to do to it, so not just the data that it was going to use, and what it was supposed to do to it, so it can have somebody else pick it up. You're likely going to have to wait for it to finish. It may impact you depending upon how many of these units of work there are, but it does enable you to not have to necessarily stop and redo all the work you've already done. RDDs and data sets are immutable. That means that you don't really change them. Rather, you apply a transformation on top of them that results in a new RDD that you then save for future use. So that's why you'll always set, if you're using Python or Scala or R, if you're doing some operation on a data frame, adding a column, transforming something, or whatever, you will need to save the data frame to a variable after that operation. Otherwise, you may have done the work, but it isn't saved, and you really don't want to do that. It is a low-level API. Generally speaking, you stay away from it, but it is there for those situations where you have to do it, right? So like many things in life, big data being one of those, if you can avoid it, by all means do so. We don't do big data just because it's cool. We do it because other things don't work. If you could put something into a database and it solves all of your problems and that's all you're ever going to do, then maybe you should just stay with the database. If it's something that simply cannot be put into a database, either because of the various type of data it might be, maybe the amount of that data or how quickly it comes along, or how big the database would have to be to do what you need it to do, then that's when you move over to something like big data systems and things like Spark. So a data frame, it is a very common use of the API. In fact, it's probably the one that most people use. And you typically do an operation similar to what you see here, where you read something into the data frame, then on that data frame you take some action to do something with it, such as pull the first 3 items. So in this case, we're doing some Scala. We're saying flight data 2015 equals spark.read.option, infer schema is true. Header is true. So that basically tells you that we're reading a CSV file, because that's what the last operation is, at a certain location, and we're figuring out what the data types of the columns are based upon a sampling of the data. You probably don't want to do that if it's a whole lot of data that you're continually doing, but there's sometimes value in being able to figure out what the schema is on the fly. It's oftentimes preferable to putting a rigid schema in place, which you can do, but there is this concept of schema drift and of evolution. So you have to think about what do you do when something new shows up, right, or changes on you. There is a header, meaning that there's a header row in the first line of the CSV. So that's what those options do, and it results in that data set being or data frame being created. Then you can, once it's in existence, you can call .take and then give it a parameter, and you're getting the first 3. So data sets are something that's only a Java and Scala thing. They don't typically do quite as well as a data frame. You can use them, but generally speaking, unless you have to, stick with a data frame. It's only one of those situations that you do it because you have to, right? So keep that in mind. Parallel programming and concurrent programming, it's almost semantics, but not quite. Concurrent programming is what we would historically have referred to as multi-threaded programming. So things are running on a single computer. They may be running with multiple threads of execution concurrently at the same time, right? So you have potentially things happening at the same time, but it's all on the same computer, sharing the same memory. So it makes your life potentially easier depending upon what you're doing. Parallel programming is distributed programming, basically. It's essentially distributed concurrent programming. It is often multi-threaded, but it does distribute things across multiple computers, right? It's sort of lost popularity around 2001, partly because of the dot-com bust, but a lot of it was because it was hard. So if you did it by hand, and wrote your code by hand, then it was painful. So that's why we use these frameworks such as Spark and MapReduce, because it makes it a whole lot easier to get up and running. You basically just say, hey, here's what I want to do, so it becomes essentially declarative in nature, and it's taken care of for you. So it's distributed across the cluster, and it just kind of works out. So things that are driving adoption of parallel programming and distributed parallel programming is in part solid state drives are fast, and they've become less expensive over time. Also, multi-core processors or virtual multi-core processors, or this virtualization of multiple cores in a single physical one, such as hyperthreading. Uh, Things around I/O improvements also have driven it. Better ways of getting data in and out of the systems. Better networks is also driving it. It's not on the screen, but it's also definitely one of the key factors, because it was a problem early on. That's part of why originally Hadoop used the cluster to store the data, because they wanted to keep it close to the thing that would operate on it. So you have a cluster that had both data and compute being done on each of the individual nodes in the cluster. Becomes a problem though, because if you want to access your data, you've got to turn on your cluster, right? And that can be quite expensive. Also, one of the things, these frameworks have definitely been driving adoption because it's so much easier to use. Also, we've gotten, even for concurrent multi-threaded sort of development, we've got better software now to help us do that. Some of the stuff that has been added to programming environments like .NET have greatly reduced the complexity of creating a multi-threaded application by adding constructs to the language, such as saying that a function is asynchronous in nature and that it returns a particular type that is a task that is a data type. So, and if you call that, you need to tell it that you want to wait for its results, not just kick it off. So, lots of things that have been driving it. So I'll go ahead and take a look at this this demo as soon as I find my window. This is hopefully not too much of a spoiler. Anyway, so what I've done, I've created a notebook out here. This is on the Databricks Community Edition. This is Markdown. If you're not familiar with Markdown, it's a cool thing to learn. It's a simplified way of writing documentation. It's a thing. There is a syntax to it, and if you Google Markdown, you'll find an example of such things like a cheat sheet that shows you how to do your Markdown. You have headings, heading 1, 2, and 3 by doing the number of pound signs. If you want something to be bold, italic. Also, if you want to do things like have tables and even images and so on. So very, very cool stuff. So anyway, that's a bit of a digression. So this is basically an example of loading a data set into Spark and then running some queries against it. So it starts off, and I'm doing this in Python. So what this does is reads a file from the Databricks file system, file store, shared uploads, and then my login, and then a file. That got there by going through either on the top level, or you can should be able to do it here, upload data, and dropping a file onto here, and it'll put it into that same location. You can see file store, shared uploads, and then my name, and then slash. And so basically drop a file on there and it shows up at that location. The DBFS is to letting you know kind of where it's at, letting Databricks know where it's at. So that's Databricks file system, and it's at essentially the root of the Databricks file system. Similar HDFS, right? The big difference though is it's a whole lot easier to get access to. And then what the next thing after we read that CSV into memory, and we tell it that there is a header, is create or replace a temporary view, and that allows us to interact with it from inside of SQL. Notice that this is an SQL notebook, right? So the default language is SQL, which means that if you don't include this magic string, and the same thing is true up here in Markdown, this is a magic string that says this cell is Markdown. So if you don't include that, then the notebook assumes that it is SQL. So we can take a look at the first 10 records just to see what it is. You can also do things like describe, and these commands should seem very familiar, having done your Hive exercise, because guess what? It's using Hive under the covers. And so this tells us the name of the columns, the data types of each, and so on. Probably should have put a option. And that way, our when we do our describe, we can see that the ints are ints and the doubles are doubles, right? So that's part of why you would use infer schema, because you might actually want to do something like add up some of these things. So if we take a look and see how many licensees there are and which ones are the most, this is a traditional sort of select statement with a group by and an order by, right? So we're saying select count star as count, so that's an alias doing our projection. Then we're saying licensee, that is the name of the organization that has that license from the temporary table that we just created at the beginning of this. Then we do a group by, the thing that we need to group by, and then order by, whatever it is we want to put it into a certain order. And as with all kind of group by operations, you can only be in this projection if you're in either the group by or you're some sort of aggregate function like count or min or max or something that basically is an aggregating function. Another way to look at that same sort of data, and this is basically doing the same stuff, but it's using a pie chart instead, and we basically told it that we want to look at the keys and the counts as the values. And it's not going to win any prizes for being the most amazing visualization that you've seen, but it's pretty handy whenever you're coming in and just taking a quick look at the data to figure out kind of what's the distribution look like. Maybe you're wanting to see a histogram or whatever. And so when we talk about things like what is the type of, so whenever they talk about the assignment asks, or one of the assignments asks, well, the top three. So what is the top three? Is that by how many licenses they have, or is it by the area that they have, right? So because having more area being covered because maybe you have a more powerful set of cell towers might be more important, right? So something to consider is that there's potentially different answers depending upon the type of aggregation that you're doing, right? And it may be different, it may not be different. This case, they're seemingly going to be the same, but there are lots of ways to figure out these various answers. If you want to do the same thing in Scala, this is one way to do it, is to use the Spark SQL command. So that's the Spark object is instantiated for you inside of Databricks. Typically is inside of Spark as well, but it allows you to get access to the Spark essentially API. That's why up here, whenever we read this CSV, it starts off with Spark. So we're accessing the context object of Spark, then we're issuing some commands against it, in this case a read and so on. So it's essentially how you access the API. Other ways of doing the Scala this is probably closer to being true Scala. So we're doing a group by operation on a data frame, and then we're doing the count, and then we're saying order it by in a descending fashion, count, and then take the first three. So limit it to the first three. And I'm not saving that in any way, I'm just displaying it. So I could set it to something else if I really wanted to, but if all I want to do is print it out, then that's certainly one way to do it. So I'll pause. Any questions? Okay. Pretty cool stuff, and it definitely makes it a whole lot easier then yeah, it's a whole lot easier than doing it in MapReduce. Right, I'll say that, because it is an intuitive sort of experience. Even the hard coding sort of using the API approach versus doing SQL is pretty intuitive. There's subtle differences between the Scala version and the Python version. This sort of Python would have challenges with that, so you have to do it a slightly different way. I believe is with a parameter or something. But there's ways to do it, and typically you kind of spend some time with Google to figure out the syntax of a particular problem. So deliverable 5, your competency is to solve problems utilizing Apache Spark. And the rubric is, as with all of the assignments, is how will determine your grade. The scenario is very similar to some of the previous ones. You're still a data scientist at Big Data Connections, Inc., BDCI. BDCI is an international data clearinghouse that provides data services to thousands of its customers. One of the major proficiencies that BDCI utilizes to stay ahead of the competitors is Apache Spark. Spark is an open source engine that typically outperforms Hadoop, and BDCI's mainstay when working with big data. I would dare say it always outperforms Hadoop MapReduce. There may be some other technologies in Hadoop that it might compete with, but and you can run Spark on Hadoop. People do. So I'm pretty sure they were meaning MapReduce. BDCI is developing a marketing plan to attract more clientele. You have been tasked to write a short paper to be distributed at a conference. Your paper will explain how Spark can crunch massive amounts of data and reveal actionable information that will allow for better programming, better problem solving and decision making. So using the provided cellular service areas dataset, create a Spark query to find the top 3 licensees and how many licensees each holds. So how many licenses each licensee holds. Your result will be reported in the conference paper. Write a conference paper that includes a definition of Spark, the rationale of how and how it works better than Hadoop's MapReduce when working with big data, and in particular when you start thinking about things like iteration and so on. Not to mention the accessibility factor kind of is pretty important because the skill sets are a significant thing with adoption of any technology. And it's much easier to find somebody that knows, say, SQL than it is to find somebody that knows Java and, more importantly, MapReduce's API in Java. So that's one of the things that is pretty cool about Spark, is it lets you, with a certain set of skills, be able to use it quite nicely. An explanation of Spark's high-level libraries and their capabilities, a definition of Spark's library components, such as RDDs, Spark SQL, Spark Streaming, MLlib, and GraphX, and Graph Frames, and how they are used. GraphX is still around. Graph Frames, similar to RDDs, is kind of being replaced. It's not all that complicated. It's basically a object that contains 2 data frames, one for nodes, one's for edges, and then it allows you to do graph operations using GraphX libraries on those graph frames. And so you can do things like figure out the page rank of a set of nodes and edges or whatever, so each individual node's importance within a network. Also, MLlib is pretty cool. It does some similar things to some of the stuff that we talk about in advanced machine learning. It utilizes, or can be utilized, to construct essentially a pipeline of operations that are then able to be executed concurrently in a distributed fashion. So cool stuff. Explain how the various components deal with SQL and structured data, machine learning, stream processing, and graph analytics to solve problems. and then include screenshots within your paper of scripts and results, along with a detailed explanation of how you got those results. So that's the instructions, the resources, and those are fairly decent. Although if you're using Databricks, the Databricks resources are quite good. A thorough and detailed paper has been written with an explanation of the advantages of Spark over MapReduce when working with big data. The paper contains a thorough and detailed information on Spark's library components, RDDs, Spark SQL, Spark Streaming, MLlib, GraphX. I would probably want to throw in graph frames and data frames, because data frames are kind of pretty important these days. And then the paper contains an appropriate and thorough, detailed explanation of how each of these components handles SQL and structured data, machine learning, stream processing, and graph analytics. One of the cool things that Spark can do for you is that inside of a table, you can actually have more complex types, such as things like a map, so a dictionary, a name value pair. Typically, you think of those in things like JSON, so that you can actually contain semi-structured data inside of what's fairly structured tables. So pretty cool stuff. Rubric 4 or criterion 4 is the Apache or the Spark Scala query was created to find the top 3 licensees and how many licensees each holds. Screenshots of the script and results are included in the paper. And with that, we've reached the end. I'll pause for questions. Yeah, you can do either Databricks or you can, if you want to do it inside of WSL, you could do that as well. But Databricks is, the community edition is perfectly fine. There's benefit to having exposure to things like Databricks, right?
Yeah, I looked into it the last time we met, so I'm trying to familiarize myself with it actually. So
Yeah.
I'll try doing this. I'll try doing this assignment with Databricks.
Okay. Yeah, and if you have questions, we can certainly talk about it. But
Okay.
it's pretty straightforward as far as uploading data, creating a temporary table, and then analyzing the results. So it's pretty straightforward.
Okay.
Sure thing. Well, thanks for joining, and stay safe. And I look forward to seeing your next submissions. So have a good evening.
Thank you.
Thanks. Goodbye.